Hey, physics students, Mr. McLeod here. I wanted to talk about this is specifically you in honors physics. I wanted to talk about the first chapter that I'm going to have you guys read through. It mostly primarily deals with the concept of what is physics, what is science, and I felt like we've already sort of dove into that. I've kind of told you what my philosophy is, physics being the study of everything in the universe and how it all works. Um, but in the beginning of the chapter, before the first set of questions comes up, it discusses an experiment done by Galileo Galilei. If you guys know of Galileo, I'm sure you've heard he's the guy who discovered Jupiter and Jupiter's moons. He didn't really invent the telescope, but he did perfect the telescope to the point that it would be usable for things like astronomy. And then he was locked away for pretty much the rest of his life as a heretic from the church, and all of his books were burned. But we now know what's left. And another interesting about Galileo is when he died, the year he died was the same year that Isaac Newton was born, and Isaac Newton carried Galileo's ideas and basically came up with a lot of the fundamental laws of physics we use today. If anyone were to ask me who is the greatest physicist of all time, I'd say Newton is probably the best, if not really close to a couple others. Some people like to say Einstein, but the number of things that Newton did is just beyond. But the experiment I want to talk about specifically right now, though, is this idea that Galileo dropped two objects of different masses from the Leaning Tower of Pisa. Now, that might be a myth. He may never actually did that. It might have been a thought experiment. But the idea that he dropped two different mass objects and that when they fell, they hit the ground at the exact same time. Now, I personally want to prove this to you, that this is in fact how things work. And it doesn't seem to follow with what most people think is common sense. If I take a piece of paper, like this piece of paper here, and I take a textbook, and I drop a textbook and a piece of paper at the same time, most people are going to say, obviously, the piece of paper is going to float down very nice and gently until it hits the floor, and the textbook's going to go bam and smack on the floor very quickly. And of course, many of you already know a lot of the reason that happens is there's a lot of air in the way, right? That air causes all these other effects like drag, and it causes the paper to drift around before it hits the floor. So, but we want to isolate what gravity does specifically. And let's say we don't want air to be a problem. So let's say instead of a piece of paper, if we were to drop, a person, let's say a person jumps out of an airplane and they're carrying a bowling ball. The person obviously weighs much more than the bowling ball. What you'll find is, as long as the person keeps their body tight and close together, is they can fall at the exact same velocity as the bowling ball. That how much they weigh has no effect on them falling. So I'm going to show you this really quickly. Hopefully prove it. My camera here. And I'm going to set it to wide angle so you get a little better view. This is my new gimbal that I purchased just recently. Okay, and I'm going to show you how I'm going to get a piece of paper and a book to hit the floor at the same time. So, book, paper, and we'll talk about why this is true. So, initially, piece of paper, book, drop them. Obviously, the book falls at a much faster speed than the piece of paper. Now, let's try something different. Let's put the piece of paper on the back of the book. Okay, so now what's going to happen is air, no, it's not sticky or anything, it's not a trick, it slides around. We're going to try to use the book to block the air to see if they fall at the same speed. If they fall at the same speed, both the book and the paper will come to rest at the same moment. 3, 2, 1, go. Pretty much exactly the same moment. So, as you can see, I've either tricked you or the objects fell at the same speed. Now, to take it one step further, I'm going to ball up this piece of paper into a very tight wad, and I'm going to try to make it so air also has no effect on the piece of paper. Okay. So, right next to each other, heavy book, light piece of paper, 3, 2, 1, drop. once again, they fall at the exact same speed. Or if we're saying they're falling downwards, we can say they fall at the same velocity. We're going to talk about the differences between those a little bit later. But what we find is that this is true, that Galileo's experiment was true. Now, why did Galileo know this? Why did he think this? There's a couple different theories behind why he may have thought this. But why does this happen? Is actually a very odd, interesting question. What a lot of people say, a lot of people like to, and it's true, but it's not a complete description, is that when things fall, it's all weightless. Falling objects are weightless. And that's true-ish. If you were to stand on a scale while in free fall, the ground would not be pushing on the bottom of the scale. And so you and the scale would fall, and because you would not be applying pressure to that scale, it would show you as having no weight, right? And so the question becomes, well, that means there's no gravity, because weight means gravity. You have weight based on your gravity. And that's not true either, because an object that has more weight is due to the fact that they have more mass and gravity pulls on that mass more. And so why isn't an object is pulled towards the earth, that should be pulled towards the earth a little harder by gravity, doesn't fall faster than an object that doesn't? And that's because we're dealing with two things at the same time, and we don't realize it. We're dealing with this idea of inertia, and we're going to talk a lot more about inertia as we go on, and we're talking about this idea of weight. Weight and inertia are not the same thing. Inertia is an object's tendency to not want to move until you push it, and its tendency to want to continue moving unless you get in its way. Like if I were to slide the book across the table here, it's what happens. Eventually, the book will not slide forever. It comes to a stop, right? It doesn't just keep going across the table. And that's because there are frictional forces between the surface of the table and the book that slow it down. So, were there no frictional forces? Were there no air in this classroom? Were there was nothing stopping this thing from moving? It would continue in a straight line forever. The way to imagine this is to say if I took the same textbook and I threw it in outer space, what would happen? And I think most people can imagine that the book would just keep floating in a single direction for all eternity until it interacted with or collided with something else. And that's actually the normal state of the universe. Things drift and travel in a straight line forever, or they maintain a singular position, unmoving forever, until something acts upon them. Okay, now, second part of that. This book is a bit harder to move than this piece of paper, and this table is even harder to move than the piece of paper. And if you notice, I'm pushing the book this way and this way. I'm not lifting it up. So the thing that's making it harder for me to move the book forward and back than the piece of paper or the table, even if all these objects had wheels on them and there was no friction or we were on ice, it would still be harder to move the table than it is the book. And it's not because they weigh more. It's because they have more mass. A general law of the universe is an object that has more stuff, an object that is made out of more stuff, is harder to get moving or to change its movement, or to basically it has more inertia. It has more than inertia than an object that, let me see if I can get myself in this scene here so the camera can see me. All right. It has more inertia than an object that has less mass. And so inertia is a strange idea. It doesn't have to do with gravity. You imagine I was floating in outer space and my massive rocket ship was parked right next to me. If I were to push off of that rocket ship, the rocket ship wouldn't just go flying into outer space out of control away from me. What would actually happen is, I'm trying to get this camera to work a little better. There we go. what would actually happen is we would find that the spaceship would move a little bit and I would move a lot because I have less mass. Okay, so what does this have to do with gravity? What does this have to do with falling objects falling at different speeds? Well, it turns out that Earth does pull on different objects different. It does pull on this book more than this piece of paper. We can prove that by putting them on a scale. This one's going to affect the scale more than this one. But while it is falling, inertia makes it harder for the book to move and easier for the piece of paper to move. So the effects of gravity pulling down on both these objects are completely and perfectly counterbalanced by the fact that there is inertia in the opposite direction. So it's hard to get this book to move downwards, but gravity pulls it down more. Those two cancel out. It is easier, it is harder for gravity to pull the piece of paper down because it's so light, has so little matter, but it is easier to move it because it is because it has less inertia, less mass. Now, does that mean inertia and mass are the same thing? We say they are. We say inertia is equal to mass. Do we understand fully what inertia actually is? Not completely. But just keep in mind that inertia isn't gravity, right? Gravity is a force that large objects or objects that are made of mass pull on each other with. And inertia is any object, even by itself in the middle of outer space, any object's difficulty in starting or changing its motion. And those two things cancel each other out in free fall. And therefore, everything falls at the same speed. This is a weird concept. I know a lot of physics teachers that wouldn't normally explain it this way, but that's because it is a very difficult, strange description. But it is exactly why objects all fall at the same speed. Now, here's an interesting fact. I'm going to put you back up here so you guys can see the whiteboard. If you were an astronaut orbiting the Earth, and by the way, astronauts orbit the Earth at around 1,000 miles per hour in the International Space Station. If you were to watch an astronaut on the space station, they would appear completely weightless. They're floating, and they appear to have no gravity. But there's a problem with that argument. If we're on Earth, and if we're in the space station, these are little solar panels here. Not the best drawing, but we're in the space station. If there was no gravity on the space station, following our rule of inertia, would just keep traveling in a straight line in one direction forever. It wouldn't keep circling the Earth. It's the fact that the Earth is pulling on the space station, and the space station wants to go forward, that it curves. And let's say, for argument's sake, that the space station wasn't moving very quickly around the Earth. It would start to go around the Earth, but eventually it would fall and hit the Earth. But fortunately, we have so much horizontal, so much sideways speed that the space station keeps falling and missing the Earth forever. So the reason the astronauts are weightless on the space station isn't because there's no gravity. They are weightless because they are in constant free fall. They are falling forever, and the only way they can ever stop falling and being weightless is if they slow down enough to return to the Earth, for the Earth to pull them inwards. So really, the trick to flying, just like the Douglas Adams said in one of the Hitchhiker's Guide to the Galaxy books, is to fall and miss. Because that's exactly what we do to stay in orbit. We're constantly falling and missing the surface of the Earth. Hopefully this helps you a little bit with the ideas that are in the first section, in the first chapter. I probably went a little beyond what we exactly needed to do. I'm going to be posting your first assignment here today, and work on that tomorrow through the asynchronous day 2, which is Wednesday. And I will get back to you with the next set of instructions on Thursday. Have a great day. Mr. McLeod out.